Hello and welcome to EE233. I'm your instructor, Gregory Myers. In this video, we're going to focus on how we can get our main to call the functions that we have written in our earlier videos. This video focuses on our P3, rather a sample version of our P3 that focuses on some physics formulas. It assumes that you have completed P2 and that you have watched the earlier videos. So to begin with, what I want to do is I want to focus on calling now our projectile 1D version 2. If you recall from the instructions, our goal was that we should be able to call this function interactively as well as parametrically. The difference being is that when we call it interactively, we are going to provide to the user a print statement indicating what it is that we expect from the user. Now, you'll get a sample of this print statement by looking at the sample.txt, and you'll see that basically I just want you to ask the user to please enter a height. And we provide for them some guidance with units by specifying in feet. Once again, the idea is that to have a nice friendly communication with the user and guide them into providing you with the correct input. We then follow that up with a scanf, and that value, although we aren't going to validate it, is then going to be passed to the function. So we're going to make a number of assumptions here. Number one, that our user is following the instructions correctly. Now, what we've got to figure out, though, is how do we collect that information from the user and then ultimately pass it to the function, and at the same time also be able to use this function with our parametric switches. And so let's focus on the interactive first, and then we'll see how we'll handle this differently, because in the parametric version, we're not going to be prompting the user. We're going to be expecting it as an additional argument on the command line. Now, the first thing we need to do, although not completely necessary, we can play some tricks, is that we want to capture it in a temporary variable. All right, I do encourage you to use these temporary variables, and more importantly, just to go ahead and declare them all at the top of your main. And so the first one we want to have is a variable to store our initial height. Now we're going to come back when we look at the other functions and we'll add the additional variables that we want to use, but we'll go ahead and initialize our initial height to 0. And I'm going to go ahead and specify the units just like we did in the earlier videos. Now, at this point, we simply want to collect it from the user interactively. And to do that, what we will do is we'll have a printf, and we're going to use the prompt that I've given you. So in other words, please enter a height in feet, followed by a new line, and then a scanf, where we specify the format spec of %lf, and we want to store it in the address of y_init. Remember that you have to use the ampersand in front of these variables to indicate the address of the variable. At this point, once again, we're not doing any sort of validation. We are going to make a call to our projectile 1D version 2, and we're going to pass to it the y_init variable. Now, if you recall, our projectile 1D version 2, as well as our other functions, all returned an integer value of either success or failure. We were optimistic. We're just going to have them return success. But what we'd like to do is we'd ultimately like to capture those return values. And what we're going to do here is we're simply going to capture our integer return as our results. Now we can go ahead and also initialize this value. And then what we're going to do is we're going to make a quick modification here results equal to projectile 1D version 2. Now, we're going to be using these results variables not only several times in this executable, but we'll also use this approach in later videos. As I mentioned, the return value for our functions isn't terribly interesting this time. We're just going to return success. So what we could do here is we can go ahead and follow this up then with a print statement, and we'll just say results followed by a %d and a new line, and we're going to plug in then whatever the contents is of that results variable. At least we get the idea and into the habit of checking the results, or at least printing the results out to the user. Now, note, this will not be the results of the calculation. This will simply be the results of our function running. So at this point, let's go ahead and build it. We've taken it for granted that our functions do in fact work. Now's the time to start checking them. We're going to do some formal testing in a later video, but we do need to know at this point whether we've got things wired up correctly. So I'm going to go ahead and change to my P3 directory, into my dist folder, debug mingw, and I'm going to go ahead and run my P3, and you'll see that there is my help. And what we're interested in specifically is going to be the 1D/I. And sure enough, we are calling our 1D with options, specifically the 1D interactively. And now we are being prompted to enter in a height. We're going to go ahead and enter in 100. And you'll see that we have a nice little table here. And also at the bottom that we are printing out results equal to 0. Remember that the constant exit success essentially maps to the value of 0. So looks like we've made some progress here. So at least our interactive one is working correctly. Let's see if we can get our parametric one to also leverage our projectile 1D version 2 function. And to do that, what we're going to need to do is convert whatever that additional argument is on the command line from a string into a double. Now, thing to notice is that everything on the command line is viewed by your C executable as a string. So everything in the argv array is a string. Now we'll get into the differences between a character vector and a string later. For right now, we're just going to take that for granted. But the point is that it is not a double, and our function requires a double. And to convert then from a string into a double, we've got a couple of ways to go about doing it. We're going to use the A to F function. And so I provided you with a link to the A to F function, as well as you can look it up on the Wikibooks site. What we do here is we simply use A to F on argv. And now this is where we need to pause for a second. We want to think, which argument should we be converting to a double? And if you think about the executable being the 0th argument, the /1D being the argument at index 1, the /p being the argument at index 2, that leaves us with our argv3 as being the one that we want to convert from a string into a double. At this point, we're actually ready to call our function. So in this case, results are going to be equal to projectile 1D version 2. We're going to pass it the y init. And just like before, we're going to do a printf, and we're going to just simply output whatever the results are from our function, followed by a new line. Now, once again, this is not going to be returning the results of some of the calculations, just rather whether or not the function itself was successful or failed. Once again, we're being optimistic in this particular example in that all of our functions return success. But more importantly, we should be able to build this. And we can now call this parametrically. And we're going to pass the same value that we would have been prompted for with a printf and a scanf, but now it just simply automatically runs, it takes the additional argument from the command line, and it passes it to our function after converting it from a string into a integer, or rather into a double. Now, we're doing no validation here. So in other words, you can easily crash your program by providing it with some unusable values, as well as you can also provide negative values. So once again, this is a fairly fragile executable. We will need to come back to validation, particularly when you use the A to F. Moving forward, though, let's go ahead and see if we can't get our interactive version of our 2D working. And so the main difference between the 1D and the 2D is that you will be asked for two pieces of information, the velocity and the angle in radians, which means that we are going to need to create two temporary or two variables in your main. So we're going to go ahead and declare a init. That's going to be in feet per second, as well as a double for theta, which will be in radians. As before, I'm going to recommend that you go ahead and initialize all of your values. In this case, your VNet and your theta, and then we can move back down to the branch of the else if that focuses on our 2D interactive, and we can print the prompt. You can borrow it from my sample file here. Please enter a velocity in feet per second, followed by a new line, and then a scanf with %LF with a format spec and simply the address of our VNet. We repeat our prompt, except this time, please enter an angle in radians, and likewise a scanf with %LF and the address of the theta variable. Now, we simply make a call using the results variable to capture the return to our projectile. (2D) version 2, with the first argument being VNet, the second argument being theta, and just like before, we want to print out what would be the results of the function running. And just to reemphasize, this is not printing out the results of the function. In other words, any calculations that might be done, that's all handled internally to the function. Rather, this is just simply printing out whether the function itself returned success or failure. At this point, I hope you see the pattern in that we can do the same thing now with our 2D parametric, and that we simply want to use the A to F function to convert argument 3 and argument 4, or argv3 and argv4, into a double, and then we pass it to our function. So careful thought here. We want to convert using A to F our argv square brackets 3, which is technically the fourth argument, and our theta using A to F of argv square brackets 4. And so just a little note here, this is technically our fourth argument because the executable itself counts as the 0th argument. And this is technically the 5th argument. At this point, we simply say results are equal to, and projectile 2D version 2, we passed it VNet and our theta. Once again, same disclaimer, we have a rather fragile executable here in that you would want to test or validate the VNet and the theta. We'll handle that later. Instead, what we want to do is we simply want to print out what would be the results of the function running using %e as the placeholder and the results variable as the value. At this point, let's go ahead and build it. We'll come back over here to the command line. We're going to rerun it now with a /2D switch. You'll notice if I don't provide it enough command line arguments, it simply provides the help. If I do /2D/I, it'll prompt us first for the initial velocity, and then for the angle in radians, and we get a nice tabular output. You can verify some of your values here, particularly that our VNet and our theta were correctly captured, but also here that our Y final is essentially really close to 0. We would have to look at a longer format spec to be able to see the lack of precision in this calculation. Basically, it's tied to round off error. We have got a combination of things going on here, but basically it's all tied to round off error. And then we have our VY init and our VY final, which correspond to each other, with the only difference being the sign. X init was 0, the X final, in other words, how far away the object landed, 310.559 feet. The X init and the X final, since our acceleration in the X direction is constant, they make sense. And then we see our results are 0. Once again, this corresponds to exit success. At this point, let's try the parametric version. If we just provide the /p, it's not enough arguments, so we have to provide the additional 2 pieces of information in the command line. And you'll see the same table now, basically without the prompts to the user to enter in the values. We're just grabbing them from the command line and converting them to double and then sending them to our function. All right, moving forward, let's do the same thing now for the beam. Would encourage you to go ahead and pause the video at this point, see if you can get this working, and then come back and verify the results. Okay, so what we'll do here is we will go ahead and make our print statements in our scanfs to be able to capture the information interactively. But if you recall from the beam problem, we have W, which is the load, L is the length of the beam, and A is the point that the load rests on the beam. So in other words, we need to have 3 more variables. They're all going to be doubles. So there will be a double W, a double L, and a double A. We're going to go ahead and initialize these. W is going to be equal to 0, L equal to 0, and A equal to 0. And at this point, we are ready to go ahead and capture the information from the user interactively by providing, once again, a series of print statements. The contents of the print statement can be found in the sample file that I provided. So please enter the load in pounds, followed by a new line and a scanf %LF, since we are going to ultimately store it in a double, that is going to be at, or rather ampersand W. At this point, you could probably get away with a little bit of copying and pasting and just some variable changes. Please enter the beam length in feet. And this would be then our ampersand L. And then please enter the location of the load. Likewise, this one's also in feet, and we simply change to ampersand A. At this point, we just need to make a call to our simple supported beam version 2 function, passing the W, the L, and the A, returning then the value exit success or exit failure to the results, and follow this up with a print statement that displays whatever is held in the results variable. Likewise, when we're calling it parametrically, we simply capture that information from those additional command line arguments. And so once again, using the A to F function and a little bit of care with our indexing of our argv. So if you recall from earlier one that our argv0 was the executable, argv1 was beam, argv2 is going to be /p, and then our argv3 will be the W, or the weight. And this is essentially the fourth argument. The L will be captured from argv square brackets 4, or the fifth argument. A we captured from the sixth argument, or argv square brackets 5. As before, this is a rather fragile executable. In other words, we would want to do some sort of validation on these values in addition to checking what the data itself looked like, or the information itself looked like. We would also want to make sure that the A resided somewhere on the L, and that L was greater than 0. We're making some assumptions here, and at this point, we're going to make a call to our simply supported beam, passing the W, the L, and the A. We then follow this up by simply printing results, %D, followed by a new line, and then just whatever is stored in the results variable. And at this point, we can go ahead and build it. And we can come back here now and we can test our /beam /I. And you'll see that not only do we get calling beam options, we get calling beam interactively, and then please enter the load. We follow along with prior examples. We have a 100-pound load. The beam is 10 feet long, and the location of the load is at 5. And you'll see that we are making a call to our simple supported beam version 2. And we print out a nice table with the W, L, and the A, as well as the 2 reaction forces. So hopefully you found this video useful. We're going to go ahead and stop here. And in the next video, we're going to look at how you're going to batch test your executable. As always, if you have any questions, comments, or concerns, don't hesitate to email me, and thank you for watching.